Robotic surgical systems. What do we know? These systems have developed rapidly in recent years, and with space exploration missions on the horizon, the subject of how we provide medical care on extended trips has been posed. A surgery-performing robot built by the University of Nebraska-Lincoln and medical technology startup Virtual Incision will be tested on the International Space Station with a $100,000 grant from NASA. Let's get into this issue. First, what do we know about NASA's big plans? NASA has ambitious aspirations for the future of spaceflight, including a desire to conduct surgery. As a result, the agency awarded a $100,000 grant to the University of Nebraska-Lincoln. The funds will be utilized to develop a surgical robot for testing at the ISS 2024. MIRA, which stands for Miniaturized In-vivo Robotic Assistant, is the name of the robot, and it may be handled remotely by a surgeon as a non-invasive approach to do medical treatments in space. MIRA is a collaboration between the University of Nebraska-Lincoln and Virtual Incision, a medical technology startup on the University of Nebraska's Innovation Campus. The Virtual Incision MIRA platform was designed to deliver the power of a mainframe robotic-assisted surgery device in a miniature size, with the goal of making robotic-assisted surgery accessible in any operating room on the planet, said John Murphy, CEO of Virtual Incision, in a company press release. The space station, in collaboration with NASA, will explore how MIR can make surgery accessible even in the most remote locations. While the trip to the ISS represents a significant milestone, MIRA will not be slicing astronauts from other countries just yet. Instead, the robot will work within a locker the size of a microwave, cutting tissue analogs and pushing rings down a wire. Professor of Engineering and Virtual Wagner built the robot's software and undertake tests over the following year to ensure that the robot survives launch to the ISS. Previous testing has included former astronaut Clayton Anderson directing MIRA from 900 miles away and the effective removal of colon tissue in surgical operations. Let us now look at the history of robotic surgery. Robotic surgery arose from the intersection of three disciplines: telesurgery, military medicine, and minimally invasive surgery. Surgical robotic systems were developed as a consequence of telesurgery research conducted by the U.S. military and NASA in the 1970s and 1980s. DARPA financed a program to create a prototype of a surgical robot system capable of treating wounded troops in distant locales. The discovery of the endoscope and the automated insufflator led to the creation of laparoscopic surgery. Laparoscopy was primarily used in the 1980s to identify and treat pathogenic diseases in the abdomen. Minimally invasive surgery, or MIS, in the abdomen was followed by video-assisted thoracic surgery in the 1990s. The robotic surgical system offered the first computer-enhanced surgical equipment in 1992. Robodoc used a pre-programmed robot trajectory to do precision drilling during orthopedic surgery. In 1994, Computer Motion Inc. created ASOP, Automated Endoscopic System for Optimal Positioning, which enabled voice instructions and surgery control of the video endoscopy. SRI prototyped the M7 telerobotic manipulator in 1996. The master-slave system was outfitted with the high-resolution stereoscopic video cameras, a 7-degree of freedom haptic system, and interchangeable surgical tools. The M7 was the first telerobotic system intended specifically for open trauma surgical operations. Current robotic surgical systems are distinguished by their accuracy and dexterity, allowing for accurate dissection, suturing, and maneuvering in restricted anatomical areas. Robotic surgical devices allow surgeons to accomplish delicate operations that would be impossible for the human hand to complete. Moving on, what is known of the famous Da Vinci surgical system? The Intuitive Surgical System Inc. Da Vinci surgical system is the only robotic system now available for robotically assisted microsurgery. A transportable instrument cart with 4 robotic arms, an imaging cart, and a surgeon control console comprise the Da Vinci G surgical system. 3 surgical tools and 1 high-quality dual stereoscopic endoscopic camera are controlled by the robotic arms. The surgical tools use endo-wrist technology, which allows for 360-degree rotations. With IOX digital magnification, the stereoscopic camera provides 3D vision, an optical viewing system, 2 telemanipulation handles, and pedals comprise the surgeon's control console. The viewing device gives a 3D image of the field, as well as real-time text information. The 4 robotic arms are handled remotely by the telemanipulation handles, which lack tactile input. However, surgeons have proved that force or tactile feedback is not required for microsurgery, since the range of motion in the operation area is small, making haptic feedback inaudible. Small incisions are used to create delicate and complicated designs. Robotic technology scales the surgeon's hand motions and transfers them into accurate endo-wrist instrument movement. movements, digital magnification, a wide range of motion, precision tool handling, reduced tremor, and reduced surgery fatigue are just a few of the advantages of the Da Vinci surgical system. Dr. Louvna excised a tumor from a patient's arm during a surgical procedure using the Da Vinci G surgical system. The system is rather massive, and its components need a large operating room. Following that, humanoid robots in space and telerobotics in space. NASA's Johnson Space Center collaborated with General Motors and Oceaneering to develop Robonaut 2, a humanoid robot. The R2 design offers a wide range of uses, including medical application like telemedicine and surgical robots. The robot may operate autonomously or by teleoperation. In teleoperation mode, the user controls the robot remotely using specialized gloves and a 3D visor. R2 performs real-time activities using stereo vision, force, and touch sensors. R2's distinguishing technology is its dexterous hands, which can use handling tools. R2 was successfully teleoperated to conduct an ultrasound scan on a medical mannequin in collaboration with medical institutions. The telemedicine capabilities of the robot were also shown by completing a guided intubation and syringe operation. R2 might work as a surgeon's helper and conduct medical operations. Telerobotic surgery has been shown to be feasible in space analog situations. Only the Earth and Moon latencies have been successfully tested. Surgical robots for a Mars expedition would be impossible due to the delay, which varies based on orbit. As a result, a deep space exploration surgical robot would need to be an image-guided, autonomous system, maybe using ultrasound, magnetic resonance imaging, or computed tomography scans. Alternately, an expert surgeon on board may direct the robot. In related news, NASA has discovered warm pits on the moon. Scientists are eager to investigate shadowed areas inside pits on the moon, which according to computer simulations, hover around a pleasant 63 degrees Fahrenheit. Unlike the majority of the moon's surface, which may reach temperatures of 260 degrees during the day and minus 280 degrees at night, the shadowed holes might one day function as human settlements. NASA's Lunar Reconnaissance Orbiter, LRO, has been measuring the temperatures of these topographical landforms, which are presumably the result of collapsed lava tubes, for more than a decade. According to a recent study, the thermal climate of the hole is more pleasant than anywhere else on the moon, with temperatures hovering about 17 degrees Celsius. Lunar pits are a fascinating feature on the lunar surface, said Noah Petro, LRO project scientist at NASA's Goddard Space Flight Center in a release. Knowing that they generate a stable thermal environment helps us to develop a picture of these unique lunar features and the possibility of studying them one day. According to NASA, lava tubes occur when molten lava flows under a field of cool lava or a crust forms over a river of lava, producing a lengthy, hollow tube. If the roof collapses, a pit may form, leading to a hollow cave. NASA stated that two of the most conspicuous holes had apparent overhangs that plainly lead to caves or voids, with a strong indication that a third pit connects to a cave. Finally, consider the surgery system in space. In 1998, the Neurolab's STS-90 Life Sciences mission was responsible for performing intricate medical operations on board the space station. These treatments included the administration of anesthesia, the management of surgical fluids, and other surgical procedures performed on living rats. The Neurolab's STS-90 missions are the only ones in history to have successfully carried out surgical procedures in space. The mission provided conclusive evidence that medical procedures, even delicate surgical procedures, might be successfully carried out in space. It may be challenging to do open surgery in space because the absence of gravity causes particles and blood to become more dispersed. Due to the elevator illusion, which occurs when a person experiences microgravity, motor responses become more sluggish. This causes movement errors to occur when reaching for an object that is seen to be located at an abnormally low height. In addition, since surface tension plays such a significant role in the absence of gravity, fluids have a tendency to become internally cohesive and form well-defined domes in this state. It is possible that doing minimally invasive surgery in space might provide a variety of benefits, including the ability to shield the patient and the surrounding environment, respectively, from biological components and particles. However, it is unknown how well injured astronauts can tolerate the increased intra-abdominal pressure caused by MIS. That's all for now, people. I hope you like the show. Don't forget to like and subscribe if you want to see more videos like this.